to have Reid from Berkeley speaking here and about Pillay's Galois theory.
All right, thanks. I'd like to thank Alice and Alexei for organizing the Colchin seminar.
And the rest of the organizers.
Oh yeah, there are many. Sorry. I would like to thank all the organizers. And I would like to thank, the CUNY Math Department in general for hosting it this year. And I'm very excited to be a part of the Colchin seminar. So, I guess what I plan to talk about today is just really an elementary introduction to model theoretic Galois theory. And my plan is to start by going through in some detail Picard-Bessio theory. From a model theoretic perspective. And then to talk about the general machinery of internality.
Would you take care of the chalk?
Yeah. So I would like to talk about internality and binding groups, which generalize the construction that I'll use for Picard-Bessio theory, and time permitting, talk about logarithmic differential equations. For algebraic groups, not defined over constants. Okay, and so this is the sort of plan for both parts of the talk. We'll see how much we actually get through. To motivate the construction of the model theoretic Galois groups called binding groups, I would just really like to revisit and spend some time going through what will amount to the binding group construction in the case of Picard-Bessio extensions. So if we have K over F, a Picard-Bessio extension, and here I'm just going to work right now in the ordinary case. It doesn't make that much of a difference. But if we look at a Picard-Bessio extension of our differential field F, and let's just assume that the constants of F are the same as the constants of its differential closure, then we can write K as the differential field generated by some alpha, where alpha is a fundamental system of solutions for some linear differential equation. So with alpha and I'll call that linear differential operator L. So now we can consider the vector space of solutions to L, which is a vector space over the constants. I guess. Right, and we'll work inside the differential closure. Now, note that, and so our goal is to understand the differential automorphism group of K over F by understanding this geometric object Z sub L. So, our goal. And so first, note that any sigma in this automorphism group is just determined by how it maps alpha. Right? And since the alpha form a basis for z sub l, we can write sigma alpha as a sum of the alpha i's with each ci in the constants. So, I guess sigma alpha I. And so this, so being able to write the image of alpha in this way gives the usual linear representation of this automorphism group inside the general linear group over the constants.
Do you really want CK or CF?
I guess in this case they're all going to be the same.
Okay.
Yeah. But yeah. And so this, of course, gives the usual linear rep, which I'll call A dash from let's see. But this is kind of missing the point, because one of the key insights of Picard-Vestio theory is that this automorphism group is not equipped with just abstract group structure, but it's also an algebraic group. And the model theoretic approach to Galois theory gives a nice streamlined way to understand how this automorphism group is imbued with geometric structure. And so our goal now is to realize the automorphism group as a, I guess I'll write constructible subgroup of GLN. But since constructible subgroups of algebraic groups are algebraic, this will give us the algebraic structure on this automorphism group. So, so our intuition is that we convert the sort of field theoretic or arithmetic structure of this group. So so we convert the problem of understanding the structure of this automorphism group to understanding the symmetries of ZL arising from the structure of the constants. And so our goal is to convert this field theoretic problem into a geometric problem. So, let's step back and try to understand how we get symmetries of this vector space from some objects having. Well, what we can do is we can use, because ZL is a finite dimensional vector space of the constants, we can use the constants to parameterize ZL. Right?
Would
So,
you remember this?
yeah, so I'm going to explain. So, namely, we can consider, so namely, for any basis alpha of ZL, we can consider the map U sub alpha from the constants to ZL, just mapping some tuple of constants C to the sum Ci alpha I. In other words, just that there exists this surjective map from Cn to ZL, right? All we've done is just selected a basis and then used a point in C to give us a point here. That's it. We're not doing anything too fancy here. Right. And in fact, using a function like this, we can also parameterize z to the n of L. Right? Where we just apply we have C1 through Cn. I mean, just using the same basis alpha, an n squared tuple of constants gives us an element of z to the n, right? So we can describe all points in z to the n this way. Now,
Really,
yes.
just to be clear, when you're speaking about C instead of C of F, so you're thinking of a larger differential scale.
Okay. So I guess what I want to do is think at the level of just the formulas. You can plug in F or F hat or anything. Yeah. I mean, if you want, we can just think of everything as living in F hat. Yeah. And so now, this gives us, in particular, a way to understand the bases of ZL in terms of this map. In particular, we can express the bases of ZL just as saying that this n-tuple is linearly independent over the constants. In other words, that the Wronskian of elements here is non-vanishing. So UA restricted to, I guess I should say UA inverse of the set of tuples x1, xn, in ZL, n, such that the Wronskian is non-zero. This parameterizes all of the bases of ZL. And by a monotheoric property called stable embeddedness, that actually gives us a constructible subset of c to the n squared. So there exist polynomial equations and inequations carving out this set. Okay, so the idea here is that we can parameterize all the bases of ZL. But now, that's not quite enough, because we want to understand we want to understand this group, and not every basis will be conjugate to another basis by some element of this automorphism group. Right? Because, I mean, we can take let's see, I guess if you take the equation delta squared x equals 0, then the basis for this 1t inside C of t will not be conjugate to the basis 2t, right? Because 1 and 2 are fixed by any such automorphism, right? So just knowing that we can parameterize the bases doesn't give us a geometric object that corresponds point for point to automorphisms in this group. So instead, what we want to look at to realize the elements of the automorphism group geometrically as a geometric object, we have to look not just at the fact that x1 through xn are a basis, but rather that they're a basis of a special kind. So first, just fix a single basis. Now, if we're trying to understand how the automorphism group can act on it, we look at its model theoretic type. So we look at what's called the type of this point over the parameters f. And now, what is the type? In the context of differential algebra, the type can be thought of just as the set of polynomial inequations and equations that hold of alpha. So in general, it'll be the set of all phi of x bar, a first order formula, such that it's true that hold at alpha.
This is the field theoretic or differential field theoretic? Type?
Differential field, yeah. So L diff. Yeah, but I mean, because of quantifier elimination, this is just the same thing. We look at all polynomial equations and inequations that hold of alpha.
Over K.
Over f.
Over F, that's
Yeah, over f.
Differential polynomials.
Differential polynomials. Yep.
So you assume that usually the type would be arbitrary order, arbitrary degree,
Yeah.
but now you're talking about linear, right?
No, this is the
L-
full type.
L is the full type,
L is the full type.
not linear, non-linear.
Right.
Oh, okay.
Yeah. But note also that alpha lives in the differential closure, right? So this means that it's constrained in Colchin's sense. Now, model theorists, when we talk about what it means to be constrained, that is to say that this type is isolated. In other words, that if we have some element beta, then beta realizes this type if and only if there's some formula in here, which I'll call phi alpha, such that the differential, or I guess the universe models this prescribed formula applied to beta. So, this means, in general, this type involves infinitely many equations and inequations. But being isolated, there's a single formula that controls it, phi. And so this phi is going to be a Colchin constructible set. And in particular, this phi will imply things like...
You mean the set of all fees?
No, there exists a single phi.
Right, but then when
Yeah.
you say it's a set, what does it mean?
Which one?
You said it's Colchin constrained set.
Oh yeah, this set. So if I mean, for instance, yeah.
Okay, with the beta
It gives
changing,
you-
okay.
Yeah,
Sure.
Yeah.
All the generic points of,
Yeah, exactly. And so this phi alpha, I mean, it will logically imply things like that beta forms a basis of ZL, but it might contain more information. For instance, in the case where we look at this equation, if I pick alpha as my original basis, then it will say that the first coordinate is 1, for instance, and that will be included in the type. So it refines this set. And this type refines it enough that we can actually understand the automorphism group. We can represent it in terms of this object. So I'll make that precise. So the model theoretic fact here is that there exists some sigma in the relative automorphism group of K over F, such that sigma of beta equals alpha, just in case beta realizes the type of alpha over F, which is the same as the universe saying that this isolating formula holds with beta. And so, in fact, and this automorphism is unique. Because we know that an automorphism of K over F, maybe I'll write it this way, is determined by where alpha sends, or where alpha is sent to. So if we have two such sigmas, they would have to be identical. So we have here, so this tells us that we have a one-to-one correspondence between elements of this automorphism group. So elements of this automorphism group to a corresponding point inside the F hat points of this formula phi alpha. And let's see, I guess the correspondence goes just by, if we have sigma, look at its, look at where it sends alpha, and then that beta is a point in here. So you just send sigma to sigma of beta.
Excuse me, let me understand this. So phi sub alpha is the first order sentence, is that correct?
That's right.
Okay. So
Or first order formula.
first order formula, right? So you are in that equivalent, you're actually using the Hilbert basis, the basis theorem for radical differential ideals?
No.
It's hidden in there.
It's hidden in the proof that
Right.
these,
Because otherwise,
that you have
you don't know
prime-
this is
Yeah.
a finite sentence.
Yeah.
That's right, yeah, a priori you don't.
Right.
So for in the general first order context,
Yeah.
you're going to use, if you're just looking at first order
Exactly.
senses, you're going to have to, first of all, assume that you have nice enough prime models, but then you would have to look at the level of the type and not necessarily an isolating formula.
Right.
So this is something special about the differential context. Yeah. Yeah.
That should be sigma of alpha.
Yes. Right. And that lives in phi alpha. And any point of this, because it isolates it, comes from such an automorphism. So now we have a geometric representative, point for this automorphism group. So, but at this point, all we've done is to define, or to think of this geometrically as a set. Now we need to realize the group law. And we're going to try to realize the group law using the structure afforded to us by the constants and this parameterizing that view.
Could you just that example? Suppose I start with alpha equal to 1 minus t comma t.
Okay?
How would that change the phi sub alpha?
So, let's see, I guess you would have, okay, so now the phi sub alpha for instance, in this case, would imply logically, so it'll be in two variables, x and y, right?
Yeah.
Now it would imply that x plus y equals 1,
Okay.
right? And so this alone would distinguish it from 1 comma t. Yeah. So picking different alphas will give us different types, but no matter what type we pick, will give us a representative for this automorphism group. So it doesn't matter which type we pick, doesn't matter which basis we pick, they'll always give us the same, abstractly, they'll all be in one-to-one correspondence here. And in fact, they'll give us the same definable binding group.
Would they be conjugate?
Huh?
Would they be conjugates?
Would what be conjugate?
The image.
Oh, the binding
Of
groups?
the sigma. The two different sigmas.
Two different.
So for one alpha. Oh, sorry. Sorry. Okay.
Yeah, so two elements are
Your
going to be conjugate just in case they have
So
the same
your
type.
sigma really is sigma sub beta, isn't it? Your sigma depends on beta. Yes or no?
Where?
Well, you said sigma alpha equals beta, so it has to depend on beta, right?
So the sigmas are just elements of the.
If sigma alpha
Alpha's
equals
fixed.
beta, then
Yeah,
beta.
alpha is
Then-
fixed.
Given beta, there exists a sigma.
Yeah.
Right, so
Yeah.
sigma depends on beta.
Oh yes, that's right. Yeah. Exactly. Which sigma?
So I
Yes.
okay,
Yeah.
okay, it's not
Okay.
one sigma works for all everything. Okay.
Yeah. I'll have to.
I
Okay.
figured out what I was bothering me.
Realize the automorphism group as in a first order way and in a reasonably canonical way. Depending on this choice of alpha, then this choice of alpha and depending on the choice of alpha, we get this identification. But now we need to define a group law. So, I guess, so this formula I'm calling phi A, I just really quickly want to change the name. I want to call this set fund alpha, which is just supposed to be the set of fundamental systems of solutions conjugate to alpha. And that's the same thing as phi A. So, now, in order to define the group law, we have now, so this set fund alpha lives inside ZL to the n as a definable set, right? Now, we've noted that we can, given U alpha, we can think of we can look at its inverse image under U alpha. And we're parameterized by some subset of C to the n squared. So if I look at U alpha inverse of C to the n of fund alpha to fund alpha. And now U alpha also, inside this constructible subset of C to the n squared, parameterizes this set of fundamental systems. And this is given by actual polynomial equations and inequations. And now, by slightly tweaking our definition of U alpha.
So you're
Yes.
assuming that that the group is an algebraic group already?
No, just this set is a subset of C to the n
But how
squared.
do you know it's defined by polynomials?
So this comes from the small theory fact called stable embeddedness, which tells you that if you have some subset of, say, C to the n, defined by parameters coming from outside it, you can define it with parameters coming from inside this set. And so in particular, any any point in here that we use to parameterize it, in particular alpha, we can get rid of all references to alpha and replace them with constants. But then there's no induced differential structure. So that means that all the differential polynomial equations reduce to polynomial equations and equations. Hence we get the constructibility.
Okay.
Yeah.
So that was called what?
Stable embeddedness.
Stable embeddedness.
Yeah. Yeah. So now, what we can do is use this function, or use a variant of this function u alpha to define for us a group operation on the set fund alpha. So, so what we're going to do is then define an auxiliary function u from, I guess, sorry, this inverse image, let's call it C alpha, say. And so now we can define a function from C alpha times fund alpha to fund alpha, where we have u of C bar beta is just u beta of C bar. So it's just the sum of the Ci's and the beta i's. And this will land back inside the fundamental sets of alpha. And now, if we want to define, our group law on this set C alpha, because this is in bijective corresponds with fund alpha, we're going to realize it as an algebraic group. And so to define the group law on C alpha, we can define it by saying that if I have two tuples of constants C1 and C2, this is going to be the unique C3 such that U of C3 U of C3 alpha equals U of C1 U of C2 alpha. Because we know that the image of when we apply their function u of C2 alpha, because C2 is an element of C alpha, applying u of alpha to C2 gets us inside this fundamental set. And then we can reapply, and because this is the fundamental set, C3, or there is some alpha, or there is some C3 such that when I compose with alpha, I actually get that element back. So because, I didn't say that too clearly, but the point is that maybe we can draw a diagram. So I'm trying to compose two automorphisms, right? I have my automorphism that maps sigma of alpha to beta 1 and sigma alpha to beta 2, and I want to be able to compose them. So sigma 1 alpha equals beta 1, sigma 2 alpha equals beta 2. And I want to understand sigma 1 of sigma 2. And that all happens at the level of fund alpha. So I have beta 1 here and beta 2 here. Now, each of beta 1 and beta 2 comes from a unique tuple of constants, C1 and C2. And we're going to use this representation in terms of constants to help us define how to compose these two elements. So these both live inside C alpha. Now, we have the equations. U of C1 alpha equals beta 1. U of C2 alpha equals beta 2. And now, when I try to actually compose using this function alpha, U of C1, U C2 alpha, that is some beta 3, also in the set of fundamental solutions. But because this is in the fundamental set, beta 3 itself comes from some C3. So beta 3 comes from U of C3 alpha. And then that unique C3 is the result of composition, and this equals sigma 3 of alpha. And so we're trying to represent composition of sigma 1 and sigma 2 in terms of the actions on the constants, and at each point it's unique, and then the well-definedness and existence of inverse and associativity all comes from the fact that we're composing this function nicely, right? We're just composing functions, and this function was surjective. Yeah.
So the goal is to use this as an example to generalize Picard-Galois theory.
Yeah.
So that you don't have to be tied with matrix and matrix multiplication.
That's right.
And things like that.
That's right. Yeah. And so the general idea is that, well, if we have these sort of covering maps almost, then we can use the composition afforded to us by the covering maps to define group operations more generally. Yeah, Alice.
And so what is happening in this example is that you are saying, I have this connection between automorphisms and n-squared tuples of constants, and I am going to willfully close my eyes to the fact that these n-squared tuples are matrices which I already know how to multiply,
Right.
and I'm going to try to recover this business of how to multiply n-squared tuples of constants from the way I'm supposed to be composing these automorphisms.
Exactly. And in the case that we're looking at here, U actually is just matrix multiplication. Right.
But one of the things that is hidden here is, for example, your matrices, you never said they were invertible.
No.
But it will turn out once this is multiplication is done that they would be.
That's right, because I mean the existence of inverses will give it to you.
You said that the original alpha was a basis.
No. In the abstract setting, in the generalization.
No, but in the abstract setting, it's the fact that it's a basis that makes it invertible.
Well, I think they will get rid of basis later on.
More or less.
Yeah.
Well, yeah. And so this gives us a well-defined group on the constants. I mean, in particular, this is just going to be a map M from C alpha squared to C alpha. And again, by this stable embeddedness business, while our definition, we used all that in order to express this defining formula for multiplication, we needed to reference alpha, right? But that actually vanishes by stable embeddedness. And so this actually gives us a constructible group law, and then we already have this definable representation into the general linear group, which actually ensures that this is an algebraic group. Yeah.
Hidden in here, I guess it's stable embeddedness again, is the fact that fund alpha is a variety. It's,
Uh,
or a constructible
It's a
set.
constructible set. It's constructible set. It doesn't have to be a variety.
Yeah, well, that wasn't my
Oh, okay, yeah,
emphasis.
yeah.
So-
That
so
is
somewhere-
the constructibility is something I don't see.
Oh,
And
that's a-
so,
that's a separate-
yeah, any,
Why is
So-
it definable?
I mean, we have a formula to define it, right? So fund alpha is this formula phi alpha. I didn't give you an algorithmic procedure to tell you what that type actually is, because this is an isolating formula for this type. So I don't have an algorithm to tell you, given this type, what the isolating formula is. But on abstract grounds, we know that there's an isolating formula by quantifier elimination and the fact that we're inside the constants. That will tell us that this is a constructible algebraic subset.
Okay, so hidden in there is the usual thing that you get this from the fact that it preserves the type of alpha. It has to preserve all relations satisfied by the basis. Gives you, that's Colchin's proof.
Well,
That it takes
slightly
the
different.
ideal into itself by,
It's slightly different
it's
in that,
slightly
in
different
that the
though.
type involves inequations as well as equations.
Well, but you can get them easily
Yeah,
from
so
the defining
basically
prime
it's
differential
generic.
ideal
Basically
and
it's generic.
one over
That's
the
what I'm
determinant,
saying.
not one over the determinant, but some constraint on that, because it's like, constraint point.
Yeah, somewhere in the definition here, as you just mentioned, the multiplication depend on alpha.
Yes.
So somewhere you have to show that it's independent of alpha, and you were claiming that that was again stability embedding.
Yeah, so it's
Yeah.
so it's not so much. Well, it does end up being independent of alpha, but that's I think for a different reason because I think there's an intrinsic version of this construction where you basically try to just define everything at the level of the fundamental sets in alpha, or just this. You pick a type and work and define the multiplication down there. So it's not so much that it's independent of alpha. It's just that we have this lifting,
It probably isn't.
and because it lifts, so if we have group
By lifting,
structure.
you mean you?
Yeah. So if we have the group structure on phi alpha, that is the group structure on C alpha, right? And then by stable embeddedness, that can be defined without reference to alpha.
Yeah. So a priori depends upon alpha, right? I mean, there's no.
Yeah.
Even by typical-
Yeah, a priori it does depend on alpha.
It is.
But then you,
Yeah. So where do you, how do you get rid of it?
how do you get, so I mean, in the sense of,
You don't?
Well, wait,
It still depends on alpha,
Yeah.
it's just that dependence can be coded up via
Right.
some parameter in the constants
Yeah.
rather
Precisely.
than alpha
Absolutely.
itself.
yeah, so for instance, if so we replace alpha with the constants that, when we apply u, give us alpha, right?
So it's always over
So,
alpha.
so then as you vary alpha, what happens to this group structure?
Oh, it stays the same.
Oh, it is actually the
Yeah,
same
I mean-
anyways. So it actually has nothing to do with alpha.
It has nothing to do with alpha.
Okay.
Yeah. And I mean, one way to see this
You,
is
mean
that,
you don't even get
It's a
a conjugation
representation that does.
homomorphism?
huh?
You don't even get a conjugation homomorphism
Between two different.
between the two different alphas?
So you get isomorphisms each way. Just, I mean, basically,
So when you
it's
say
in terms
they don't
of
change, you mean
this
they're
group law.
isomorphic.
right, because we. Think of how if we had two different alphas and betas, we can draw a picture to try to see what the group law should be. That'll give us the isomorphism, right? So
It's by a
let's.
change of basis conjugation.
In this case,
In
yes,
this
but there's a
case, yeah.
more general model theoretic way to
Right.
see it,
Okay.
just using this function u. So let's go through that. So here, let's just identify everything C alpha and C beta, say. And so there I'm using the same function u, but in general you don't even need to, you can
Well,
have,
I think that, would you mind not using beta here? Because
Sure.
I would get confused.
okay, C alpha 1, C alpha 2.
Okay, that would be better.
Okay. So then,
Actually, that's not good.
okay,
Gamma, C alpha and C gamma,
C alpha and C gamma. Okay, so now,
because you have alpha 1 up, you know.
so we're going to try to end this equipped with the group structure. So can I call the group structure N alpha
Right,
and gamma?
right.
Okay, and we were trying to construct an isomorphism theta,
Sure.
right? So now,
No, if you say they're isomorphic, I'm fine, but you have constructed
abstractly via, I mean, I'm going to construct it definably. Because we know that these are both abstractly isomorphic to the automorphism group by this construction,
Right.
right? So that's
Well, I would say isomorphic. You defined two different group structure on this set called automorphism.
No. So this set is just honest to God automorphism, differential automorphisms of K fixing F. Then we
Okay.
represented it geometrically in two different ways.
Okay, so it's actually
Right.
it's isomorphism.
Yeah,
Okay.
and the point is that we constructed this M alpha in the way that this guarantees that the group law is composition so that it's compatible with the action of sigma on
So that
this
has
set.
that.
But basically it just comes from the fact that we're defining everything in terms of composition
Okay.
of functions.
All right.
And so when we compose the two automorphisms, that's just the same thing as composing U twice.
I agree. Okay.
Yeah. Yeah. And so now, I mean, let's just
Well, then
investigate.
you just do a composition of it.
Yeah, but we want to know that this is perhaps
Well-
definable, right?
Well,
So these are
but-
abstractly.
Okay, so the stability embedding would do it because the inverse would be also definable.
But what is this map?
Oh,
I
so,
mean-
so you take one of them and take the inverse and just go through it.
But this is not a definable object. This is an abstract group. I have two definable groups.
Ah,
They're isomorphic to some abstract group, but they might not have the same structure. So for instance, I mean, a priori you could have two, I mean, you can have two groups with different geometric structure
okay, so
that are
you're saying-
isomorphic to the
okay,
same
so,
group,
so
right?
let me understand. So you're saying that the isomorphism is on the group level, not algebraic group level or anything.
Yeah,
Just
yeah. So
group-
this
just
just
group,
tells us that
abstract
the
group,
isomorphism
abstract
is at the group level,
As in group,
abstract.
as in group theory.
Yeah, but then
Okay.
this theta will
Will
preserve
be
algebraically,
okay.
right?
Got it.
And I mean, the way that we do that, I mean, they'll be rationally isomorphic, so
Right.
algebraically isomorphic, and then we, but how we're going to understand it is through this map.
And then you can induce the algebraic structure on this automorphism. Okay.
Yeah. So then the point is to, I mean, if we take some C bar, that,
But okay, so I mean, C alpha M alpha is already a definable thing,
yes,
and it is an algebraic group, right?
yes.
Okay, so this is being group isomorphic. You can simply just carry the algebraic structure over, no?
Yeah, but how do you know that they're compatible? Compatible algebraic structures on the automorphism group.
Well, yeah, one.
This is what we need to
then,
show.
And then if you so by definition, the inverse is also a morphism
inverse you
of
don't
algebraic
worry
groups.
So okay,
Is
so
it,
here's
is it or not?
Once you get
Uh,
multiplication, you get inverses free.
Suggestion.
Yes.
It's algebraic.
Yeah,
Grab a
right.
color.
yeah.
No,
color
I mean the
things that are
the group
algebraic and color
isomorphism
things that are
itself
abstract, different colors.
is also
Okay.
a morphism.
So abstract, abstract.
Right, abstract, right. But
And
now,
then
but
what we
now
want is algebraic.
right.
And so here's the worry, right?
So as
this,
algebraic,
this might have algebraic
No.
structure here, and if we try to induce it here, they might not be the same algebraic structure
what do you mean?
up here.
Okay, so look, you can take two elliptic curves with algebraically independent transcendental
Yeah.
J invariants. They're isomorphic as abstract groups.
But they're not
They're both
isomorphic.
isomorphic to z hat cross an uncountable thing of blah, an uncountable number of divisible abelian groups, an uncountable dimensional vector space over the rationals.
But they are.
But they're not isomorphic as algebraic groups because there's no isomorphism between them because that would force the J
It
invariant.
tends to be the same. Yeah. Yeah. So all we're doing here is just trying to check the compatibility of the algebraic group structures, right?
Okay.
And it basically just amounts to trying to define a formula from C bar, or trying to define some constructible homomorphism here, right? And I mean, the way that you do that, well, so if we have C bar is coded up, the way we go from C bar to the automorphism group, right, is it gets mapped to the unique sigma, such that sigma of sigma alpha, or okay,
No.
The other way, the C bar.
Wait a minute.
You.
we're trying to go from C bar
The
to
uniques.
an automorphism, right?
Right, right.
And so, so it's the unique sigma such that sigma alpha equals U
That's right.
alpha C bar, right? But then this U alpha C bar,
Right, right.
You mean C bar alpha?
C bar alpha.
yes. Yeah, but this C bar alpha, that's something that we can define first order, right? So now, given U of C bar alpha, we can map that to the unique D bar such that U of D bar beta equals U of C bar alpha.
Gamma.
Yeah.
Yeah. Yeah. Right.
Come.
But then
Okay.
saying the unique D bar such that this equation holds, this was all first order. And it defines an isomorphism. Right? So we are going through the automorphism, but what we need to do is to check that going through yields a definable relation, which it does. And once we have that, we have our constructible isomorphism, so they have the same algebraic group structure.
And the multiplication, this works.
And the multiplication.
Just check that this
Yeah.
D bar assignment.
Right. And I mean, checking the composition is basically, well, this is function composition. This is function composition, so it preserves everything. Yep. So that part's
How
not
is
too
that different from what I said?
bad. I mean, it was just that it wasn't automatic that I maybe I'm misunderstanding, but was what you were saying is that take this, transfer algebraic structure here, and it automatically agrees with this or something? I mean, the worry here is just that we have two algebraic groups that are abstractly isomorphic. They need not be algebraically isomorphic. But by going through this composition, we can see that this constraint is actually an algebraic
So you're
constraint.
saying when you explicitly write it out,
Yep.
then it becomes definable.
Yeah, because it happens to just
Okay.
do this.
All right.
It happens to be of this form, which is what we need to guarantee that preserves the algebraic structure. That's it.
Oh, okay. All
Yeah,
right. Got it.
because we want to imbue this unambiguously with algebraic group structure. Here's the possible ambiguity, and we got rid of it. Yeah, and then a similar argument shows that it didn't matter what U we picked, so long as it was surjective and whatnot. So I guess now with all of this in mind, I'll just present the definition of, or I'll present the model theoretic generalization of what's been going on. So, all right. So the main players here are what are called a concept called internality, which basically plays the role of U. In this previous construction. And binding group, which plays the role of C alpha, M alpha in this previous concept. So these are the two examples to keep in mind from the Picard-Vecchio setting in order to understand the model theoretic generalization. And so again, what we'll talk about in the afternoon section is about how you can realize Pillay's Galois theory, or you can realize differential Galois theory, strongly normal and more exotic Galois theories in terms of this internality and binding group construction. And what we're going to do right now is just take a step back and try to answer the following question. So given two definable sets, X and Y, for this case, the two Colchin constructible sets, we can ask the question, the vague question, what are the symmetries of X that arise from its relation to y. And what is its geometric structure? And the mathematical question, really formalizing this, is trying to understand the structure of automorphisms of x fixing y. But again, this is somewhat vague. So in the first order context, I'm going to assume that we're working in a theory T that has prime models. I guess has unique prime models.
Over sets or?
Hmm?
So he's thinking over sets?
Yeah, over sets. And this condition holds in the cases that people in the seminar will care about. So for instance, DCF 0, 1, or DCF 0, m satisfy this constraint. And
unique up to isomorphism.
unique up to isomorphism, yes. And I mean, here the prime models are just going to be differential closures. And then the group of automorphisms we're going to look at is precisely the automorphism group of M fixing all the M points of Y, where M is the prime model over some set. But we want to look at symmetries of X. So I'm going to define this auxiliary group, aught sub X, which is just the set of sigma restricted to the M points of X, such that sigma is in aught M over Ym. So we're just looking at the restrictions of automorphisms of the full structure to the points in X.
Could you give the example of the Picard said what role is X and what role plays X and what role plays Y?
Yeah, so here we're looking at symmetries of the vector space, ZL, arising from its relation to the constants. So Y, so here, Y plays the role of a parameterizing space, and X plays the role of the space that's being parameterized.
And what would be M here?
The M, the group.
M, capital M.
Right. M will be the differential closure. So F hat.
F hat.
Yeah.
So it's constant of F hat here.
Yeah, but then the role of X will be that, well, if I want to understand an automorphism of, so I have an automorphism of the differential closure, but I'm really interested in automorphisms of
Down below. Right.
But then,
L.
because I'm looking at the restriction to X, I guess the restriction to the space of solutions of the differential operator, that's the same thing as the automorphisms of a basis for X. So that's why when we restrict to X, we're then looking at automorphisms of the Picard-Vessio extension fixing the constant points.
Okay.
Or, I guess, fixing, together with F. Yeah, because implicit in this, I guess really I should say that we're looking at the models where we have some underlying field F. So we're allowing, this is just saying differentially closed fields containing F or in single or multiple community derivations.
So
Yeah,
so
Is it sorry.
you go ahead.
Is it obvious that every Picard-Vessio extension can be over F can be embedded in the differential in a differential closure of F?
Is this
Or do you just take them from a given differential